I'm going to be talking, my main interest is broadly in lighting and in human behavior. But actually today, I'm going to report on some work that we've been doing that shifts much more to the urban scale and try and cover some of the key directions and questions in a way that we've been addressing in our work recently. And it probably goes back about 10 years, but I'll cover it quite quickly and really want to cover these questions or topics that were mentioned before. I think what's beginning to happen now in the conference, that people are making increasingly able to make connections between presentations, and certainly some of the information, some of the examples that Henning Larsen, architects Singer Kongebro, I apologize for my pronunciation, gave on urban density and energy use are relevant and are reflected to an extent in our more theoretical work in Cambridge. But also Peter Head's introductory talk today talked about an attempt to create a comprehensive econometric social model of urbanism. And I'm going to report fairly quickly on a 5-year project that's just finished that has done exactly that, I think to a large extent, and starts to reveal some interesting results in terms of the sensitivity of the various parameters. So I'll talk about density and energy. Diversity is a topic that came up earlier today, and then look at some future scenarios, how different strategies with respect to urban development are impact on energy in particular. About 10 years ago, we started looking at ways of mapping the urban environment using digital elevation models, 2.5 dimensional, 3-dimensional models, and using MATLAB to do various, act on these maps and do various processes. And this is just an example of 3 maps from actually a piece of Toulouse. On the left, we use the analysis, the image analysis, to determine the orientation and the depth of the daylit or the climate zone in each building. In the middle, there's a definition of the level of obstruction adjacent to that facade, whatever orientation it is. And on the far right is a simple, based on a number of parameters like spacing and orientation, a simple prediction for the energy use in terms of lighting, heating, and cooling, making lots of assumptions about individual buildings, in fact standardizing the characteristics of individual buildings quite extensively. Because we were interested in seeing how urban form influences energy use, we know a lot about how double glazing or insulation or natural ventilation influences energy performance of individual buildings, but we were interested to see specifically what the effect of urban form was. And just from that simple analysis some years ago, we can plot the density on one axis across the bottom and the effect on the energy use if we assume that all these buildings were office-type buildings. And we can see that as you increase the density, you increase the energy demand. And I think, this is, in a way, raised for us the question, well, is that necessarily the case? And as I say, Henning Larsen architects demonstrated that there are ways of getting around that, still increasing the density, but managing to achieve lower energy consumption. So from this simple plot, you can see that if you double the density from, say, a plot ratio of 2 to 4, you increase the total energy use by about 25%. And you could say, well, this is a bit worrying because actually there's a big push for increasing density of our cities. Urbanization is increasing, we can't keep expanding our cities, so the density is increasing. And so the question arises, how can we overcome this, or how can we tackle this challenge? How can we create a socially diverse and dense urban environment that uses less energy? Because the pattern is that you will use more energy. If you do nothing else except increase density, you'll increase the energy demand. So we carried on developing mapping techniques for looking at various simplified climatic parameters, which included wind and solar radiation and temperature variation. And we realized quite quickly that you could then map thermal comfort outdoors using these kinds of parameters. And we started exploring ways of mapping comfort and then creating what we call a kind of diversity map the different conditions you find in an urban environment. We tend to think of an urban environment as a kind of a uniform kind of environment, uniformly slightly warmer than the rural environment, for example, especially at nighttime. But clearly, there are shady bits, there are windy bits, there are bits that are in the sun, there are bits of the city that are protected from losing heat during the nighttime and stay warmer at nighttime. So by trying to map this diversity, we then wanted to see how that related to people's perception of outdoor comfort. And this is a little bit of a tangent, but this kind of mapping work builds up. And we found some interesting correlation between asking 10,000 people in different urban environments about their satisfaction level, or their desirability, and the diversity of environmental conditions. And we found an interesting effect, that there seemed to be a correlation. The more diverse your urban environment, the more choices you have in terms of sitting in a sunny space or a shady space or a windy space, etc., the greater the level of satisfaction, or the greater the desirability appears to be. And that was sort of confirmed in another related study. Sorry, this is the one where we interviewed 10,000 people and asked them for their actual sensation vote on the left with respect to comfort, so that as the diversity increases, their sensation vote approaches comfort. So they perceive the more diverse urban environment to be more comfortable. And I think that's a really interesting idea with respect to diversity. And it made us think more about how you create that diversity, what urban form parameters there are that might affect diversity, and how that diversity then not only relates to the comfort conditions in the street, but also the energy performance of the buildings that create that diversity. So we started typically of the Martin Center. For those of you that know the Martin Center, we started working on very simplified arrays of buildings. So we took a very simplified set of conditions and then started to play about with having the same overall density, but changing some of the parameters with respect to variations of height and variations of spacing, just to see what would happen. And we get, and this is, I apologize, this is slightly difficult to read, but we get some interesting results. So on the left here, on the bottom line, we have the density. So we have low density to high density, and here we have an indicator of daylight availability, the sky view factor. And we can see that a low density array like this has, in this case, a sky view factor of 0.2. And if we increase the density, we have less daylight available, and hence the energy use would increase. But if you cut across and you say, let's see, if you want to double the density, but maintain the same sky view, the same availability of natural light, you come to somewhere here. And actually you find that introducing a degree of randomness with respect to spacing increases the availability of natural light and in fact solar gain. And this really confirms at a sort of fairly abstract and theoretical level the intuition that Ms. Koen spoke about with respect to Henning Larsen's projects. And we can then, from that kind of analysis, we can then draw some simplified conclusions that urban diversity with respect to the horizontal spacing is preferable to having very regular arrays. And from the modernist period, we tended to think in regular array terms, very functionalist terms. Low site coverage, and therefore having higher buildings or variability in height is also preferable. And that actually these simplified arrays are not very good at explaining the real urban environment. Because even just from looking at this way of making an urban array a bit more complex by varying heights and spaces, we can see that that has a big effect, potential effect on the daylight availability and the sunlight availability. So imagine what would happen if you look at a medieval bit of city instead of a series of blocks. You'd get, obviously, potentially much more interesting complexities and variations. Now, the core part of my talk today is really now to start to look at the existing, and this reports on the work we've done most recently, look at the existing building stock, our existing cities. In this case, we've been working on the southeast of England with a focus obviously on London, but including places like Cambridge and Oxford and Peterborough and other nearby towns that are developing. And we have developed this, this econometric model that looks at land use and transport and imports projections with respect to demographic change, with respect to employment patterns, with respect to government policy about refurbishment, for example. So we've built this, this model that I think is not dissimilar from the one that Peter Head spoke about first thing this morning, and started to test some of these parameters. And one of the things, the way we wanted to explore this was to look again at density versus sprawl. So we looked at these strategic options. On the one hand, you could go for a compact development, keep the city more or less from spreading and go up or fill in the gaps, to a linear set of expansions adjacent to the city center, to a much more free market approach where you say, well, anybody can build anywhere and see what happens to the economic indicators, the environmental indicators, effects on transport, and what I'm talking about today really is primarily the energy implications. So this is an example of compaction, fairly high density, fairly near to the urban centers, to urban railways, with employment mixed in with housing. A market-led approach is where you start to look at urban extensions on the edges of towns, which are easier and cheaper to build on and preferred by developers, probably, to much more rural kinds of developments. And I think really what we're trying to say is that, is urban compaction always better, or actually can rural development and sort of intermediate satellite towns be useful alternatives to complement urban compaction? So let me now turn to the energy model, specifically the building energy model, and I'll skip through this fairly quickly because I think it's a little bit heavy going otherwise. But basically, it's a combination of a building stock model, taking all the data we have about the UK's housing types, ages, conditions, etc., and a sort of bottom-up building physics model, a building energy model, to determine the energy use of the whole of the UK's building stock, and then compare that with real data that the government has on building performance, and particularly in this case domestic performance, although we've extended that to non-domestic as well, and effectively validate the model against that. And this is just some examples to give you a degree of perhaps of reassurance that the validation process is going on in the background, with strong correlations between the modeled and the actual performance. And perhaps it's worth stopping here for a moment, because this is an example of the kind of output of the model. So this is all based on the existing housing stock. And if you plot density here against energy consumption per dwelling or energy consumption per square meter per dwelling, if you look at that red line here, that line is the energy use per square meter of the UK housing stock as a function of density, which I think is a very interesting feature. So on average, and there's a lot of spread clearly, but on average, the UK's current housing stock consumes the same amount, almost, and it's the same amount of energy per square meter, independent of density. Now, obviously, we have smaller buildings in cities. We have apartments rather than houses, so the dwelling size is reduced. So if you do energy per dwelling, you do get a reduction in energy use. As the density gets higher, there are less, more dwellings per hectare, and therefore a less square meterage per dwelling, and therefore reduced energy consumption. So I think this is, for us, it was a really interesting a problem, because we were interested in looking at, well, what happens for different kinds of development, and this suggests, the top line at least, suggests that actually it doesn't really matter how dense or not, or compact your city is. Energy use per square meter, at least assuming the existing building stock remains the same, is the same. And therefore, you could create good rural sustainable developments and good urban sustainable developments. And this is just, again, some output of the model that shows some of the parameters, some of the sensitivity analysis of our model, which is confirmed by other work, by the way. This isn't a uniquely Cambridge model, but there are other models that reflect the same kind of results. And this really just shows, and I want to just point out that in terms of sensitivity analysis, that if you change the average internal temperature by 1%, you have a big effect on the CO2, I think it's the CO2 emissions. So the most sensitive parameter with respect to our building stock is the occupant's choice about the temperature of their house. And if you imagine, 35 years ago, the average household temperature in the UK was 12 degrees, the average, so including the bedrooms that were usually unheated and the living room. Now the average household temperature in the UK is about 19 degrees. That's a major increase in thermal expectation and a major increase in energy demand. It's effectively doubling the energy demand if everything else remains the same. So the biggest single parameter, from our work at least, is occupant behavior and occupant expectation with respect to comfort. The other parameters are less sensitive, and I won't discuss them in any detail here. So what we then wanted to do was to map the whole of the UK and to look at new options for expanding the UK. And we developed a whole series of ways of defining typical types of tiles, we call them urban tiles, that you could combine to create a representative bit of city that could be either high density or low density or mixed use, etc. And these represent the existing housing in the UK for different densities. And this is just some examples of the energy demand for the current energy demand in the dark red bars in the UK for these different clusters. So you can see that there is quite a significant variation in the energy demand per dwelling, as I mentioned before. But the most significant change is actually whether the dark orange bars, whether you retrofit or whether you have a new build, that has a very profound effect, as you might expect, compared to the base case. Retrofit, refurbishment, and new build are going to have much more a very significant effect compared to whether you have a sprawling city or a compact city, for example. Although there are clearly benefits in having a compact city. We employed the government's retrofitting measures in terms of their ambitions, in terms of the take-up of the anticipated take-up of different retrofit measures in our model to predict what happens with our 3 scenarios over 30 years. And this is just showing from our econometric model and our employment model where these houses would be with respect to, in this case, in the southeast of England, with London in the blue here. So you can see that the trend is fairly spread. A compaction model is where you don't allow that so much, and then a market-led model is even more free-ranging. And we use that as a basis to then model the energy consequences. So having our building energy model, having our dispersal model in terms of development, we could then compare these different trends with respect to urban development. And these are just 2 examples of, for example, if you go for compaction, then clearly there's a lot of increased energy demand in the urban cores. If you go for market-led, then you get more spread around the region and around the edges of London, in the suburbs of London, where people like to live, typically. That's where the energy demand will be. And the pattern of urban development will be very different in the core to the suburbs, to the rural environment. And therefore, one would expect the environmental strategies to be very different. I won't describe this in too much detail. There are non-domestic models, and again, a prediction about the spread of development and energy use for retail and industrial and other types of buildings. And I'll skip to, this is the final sort of result of the model, including all building types, and basically the same pattern repeats again, because domestic dominates, that you get this very different dispersal of energy demands. And then we wanted to compare that to, and I'll do this very quickly because there are other people who've done this kind of analysis before, but we wanted to compare that to the solar potential of the urban environment. And if you look at London, you can see that in the center of London, the solar potential is much lower than in the rural environments. So solar energy is particularly suitable for more suburban developments, where the demand is also a little bit lower and more spread than the concentrated city. So you'll never meet your demand with solar energy if you try to do it by putting PV on city center buildings. And then we looked at various variables, and again, I'll skip through this very quickly, but looking at urban parameters, building parameters, and how they then influence the solar energy on the facades. And you get a similar pattern, that the amount of solar energy available on facades is clearly much greater in the environment around the high-density city centre than in the middle. And I suppose if I were to come to a conclusion, these are the key points I would like to make. That at the aggregate level, at the large regional scale, the basic patterns of urban development make relatively little difference in terms of the energy demand in buildings. And in fact, the same happens to be true. We had transport modelers modeling the same effect. The same happens to be more or less true, that we're talking about a 5% variation of effect for transport energy. And that's largely because the infrastructure is there, and it's not going to change very quickly, even in 30 years, even if you have a complete policy dominated around compaction versus market-led policy. As I've mentioned before, the energy implications are spatially relevant, so different energy strategies are relevant in the third point here for different regions. So as I say, in a more open area, you can exploit wind, you can exploit solar. In a more compact urban area, you might look at heat networks and ground source heat exchangers and combined heat and power systems. What we are finding at the neighborhood and building scale that the decisions are really very influential. So whether you refurbish or not is much more important than whether you have a slightly more compact city or a less compact city in terms of energy use. And things like occupant behavior, educating, giving occupants feedback about their building performance are all parameters at the level of individual buildings that are critical in terms of the final energy demand. I think at that point I'd better stop, and thank you very much.